So, which is faster, hot or cold? The answer is hot. You can catch a cold. I'm here all week. Okay, getting back. So now when we take a look at intermolecular forces, we've done two ions, but now we're going to take a look at just some covalent bonding or dipole-dipole. And so dipole-dipoles occur when you have two polar molecules like HCl, and what happens is the negative side will be attracted to the positive side. And so you kind of make this all throughout the species, the IMF, or the intermolecular forces, the positive and the negatives attached together. Notice we have a dotted line, which basically means an intermolecular force. Once again, it's going to be almost 10 times weaker than that of a chemical bond. Okay, and so what you'll see is if you have two polar molecules, you'll have this intermolecular force, and things are good. What's interesting is that you'll have an unusual case, and this is called hydrogen bonding. And what happens is when you have hydrogen and connected to some very electronegative atoms like fluorine, oxygen, and nitrogen, I usually like to say H-Fon. You get a stronger interaction, and what happens is the hydrogen's partially positive, and this partial positive is going to interact. Let's take a look at water and what happens is this partial positive end of the water, I shouldn't have made that a plus, let me erase that. This partial positive will interact strongly with this oxygen. And so you get a very tight interaction, and it's because it's also pretty small, you get it very close. And so this hydrogen bonding is usually one of the strongest intermolecular forces. When we start talking about dipole-dipoles, not dealing with ions at all, we're just talking covalence. Okay, and so an example of this, once again, is this hydrogen sees this lone pair on the nitrogen, it's very strong. This is similar to that of water, and so when you have this type of interaction, you got hydrogen bonding, and so you need two things, as again, you need fluorine, oxygen, or nitrogen, and you need lone pairs on those species. Okay, and so where do you see some of this? Well, let's take a look at, for example, if we take a look at the periodic table, when you have oxygen, sulfur, selenium, and tellurium. And so what happens is, because in general, as you increase the molecular weight, you would expect the intermolecular forces to get stronger. But notice, so if oxygen did not have hydrogen bonding, it would be something like this, because this would be the trend. But because of this hydrogen bonding, you get a very strong interaction, and so this is a lot stronger. The IMF for water is a lot stronger than the IMF for H2S. So notice the water is way out of the range, following the trend, hydrogen bonding. Okay. The other thing that you'll see is because of hydrogen bonding in water, you get what we get. You have capillary action, surface tension, and it's the reason why ice floats. And we'll get into that. But for the most part, this hydrogen bonding is pretty strong, and so that's the reason for the capillary action. Capillary action is when is what you see when you read a burette. You get a meniscus. Surface tension is going to be on the top of water, especially over the summer. That's why you see little bugs on a pond in a lake, and then ice floats. We'll get into in a second. Okay. So why does ice float? Because it's less dense than water. So the hydrogen bonding allows in water in the liquid phase allows it to get closer than normal non-hydrogen bonding liquids. And so because of that, water's maximum density, don't forget, density is mass over volume. So what you'll get is, in the liquid form, you get kind of like you get the maximum density of 4, and then when ice freezes, because of the structuring, it actually expands, and so the ice has a larger volume than water, liquid. And so because of that, the density of water is less. And so it's one of the few substances that has less dense than the liquid. And that's because, once again, in the liquid form, because it's not a rigid structure, the water molecules and the hydrogen bonding can get really close and tight, which decreases the volume. But as you make the solid, it forms a rigid structure and the lattice, and that is less dense than that of the liquid, which means ice floats. Okay, so the other place you'll see this in like all your alcohols. So when you do lab this week, you'll notice that the alcohols, the methanol, ethanol, propanol, 1-butanol, is going to have a stronger intermolecular force than that of the non-dipoles, hexane and pentane. But you'll also see this in the following. Ethanol has this oxygen here, this hydrogen here, and you form the strong hydrogen bond, and you get a boiling point of about 79 degrees. Over here, you do have an oxygen, but there's no hydrogen connected to that oxygen. And because there's no hydrogen here, you do not form you form just a dipole-dipole, and that dipole-dipole is not as strong as the hydrogen, and you get a boiling point of minus 25. The higher the boiling point, the stronger the intermolecular force. Okay, so now the next one, as we go down for weaker, is dipole-induced dipole. So what is this? This basically is the reason you have a dipole species that kind of influences a non-polar species. And so the classic example is going to be like carbon dioxide in water, and so, or oxygen in water. And so what happens is this oxygen has no dipole, but when it gets close to this, it's almost kind of like a magnet. This causes a little bit of an interaction here. It kind of influences and induces a positive end and a negative end. And so what this allows for, like CO2 to dissolve into water. It also allows for fish to breathe underwater, because what happens is the oxygen is dissolved into water in a very weak interaction. Okay? And so the oxygen, so the gills in a fish extract the oxygen from the water because it's a really weak interaction, and so that's why fish can breathe dissolved oxygen, and it allows for fish to breathe underwater. The big problem is that warm-blooded animals, it just takes, you don't have enough oxygen in the water so that's why whales and other things breathe above water. So the last one I want to talk about is just when you have two nonpolar species. And this is really weak, and it's the weakest of all forces. It's also known as London dispersion forces. It's also known as van der Waals forces. And this is, once again, the weakest of all. And what happens is when you have two nonpolar species, once in a while you get a distribution, an uneven distribution of electrons, and then that will induce a interaction. And so, but it doesn't last for that long. And so let's take a look. So you have two helium atoms. And so atom 1, atom 2. Notice there's no interaction. Then all of a sudden, this B atom has the two electrons on this side. So it creates kind of a minus, and this creates a kind of a plus. And so when this happens, the atom A then sees this partial negative, and these two electrons here form a negative, and you get this interaction. And so then it's held together. But this is, and so this B induces an A, but this is weak. And then what can happen is shortly it just disappears. And so it's weak. And so, but how does the strength work on this? Well, as you increase, there are two things. As you increase the polarizability or the size, the induced gets stronger, and then the shape. Usually what we say is the following: the larger the molecular mass, the stronger the attraction. So if everything is being equal, if you have two species, like for example in lab, you're going to have pentane and you're going to have hexane. Okay, hexane has a higher molecular weight, so this is going to have a stronger intermolecular force compared to the pentane. So if you have two similar forces, like dipole, induced, then the molecular mass will determine which one is going to be stronger. Okay, so higher molecular weight, larger induced dipole. So for example, as you go down this chart here, as we increase the molecular mass, notice that the boiling point gets closer and closer to zero. That means this is stronger. Okay. And so in summary, and this is where I'll end, you have the following: that in ion dipole, and we have hydrogen bonding, dipole, induced dipole, and induced dipole. So as you go down, the IMF gets weaker. And we're going to get onto this in class on Wednesday, but I'll put this in the across from my office. But I like this flow chart. This will help you determine the intermolecular forces, and then down here is kind of a reference. And we'll get into that. So enjoy your rest of the day. I will see you on Wednesday, and have a good rest of your Monday.